Hi everybody, Dr. White here. We're going to introduce today the second major topic in this chapter, infinite series. I want to take you back to that example of the cake, the one that you eat a little bit of every day. And remember, on day one, you ate half of it. And on day two, you ate a fourth of it. And then day three, you ate an eighth of it, and so on. And the amounts you ate each day were an infinite sequence. I want to consider another infinite sequence related to that. I want to look at how much you have eaten so far by the end of each day. So like at the end of the first day, you've eaten half the cake. By the end of the second day, you've eaten the half you ate on the first day plus the fourth that you eat on the second day. By the end of the third day, you've eaten the half plus the fourth plus the eighth that you eat on that third day. By the end of the fourth day, you've eaten the half plus the fourth plus the eighth that you ate on earlier days, plus the 1/16 that you're eating today. And it goes on like that. So it's another infinite sequence, okay? It's a sequence of what we call partial sums. You see, we are summing the members of the original sequence, but stopping at a certain point. It's just that every time we stop a little bit later. Partial sums. We can get a formula, a general term, for this sequence of partial sums. We call it S sub capital N, S for sum, capital N for how many things we're adding up. So the general formula, 1 over 2 plus 1 over 2 squared, all the way up to plus 1 over 2 to the n, could be written with sum notation. Sum little n goes from 1 to capital N, 1 over 2 to the n. When we write the general terms of the original sequence as an, then we could say that the partial sum is the sum, little n goes from 1 to capital N, of a sub little n, okay? Now, for this particular sequence of partial sums, I'd like you to notice that it's an increasing sequence. And that's because every time the number that, the extra number we're adding on to what we had before is a positive number. Second of all, this particular sequence of partial sums is bounded above by 1. And that's because no matter how many days you've been at it, you can't have eaten more than the whole cake, So your total amount eaten can't be more than 1. So actually, by the monotone convergence theorem, we know that this sequence of partial sums must converge to some number that I'm going to call S. Or we could write limit as capital N goes to infinity of S sub n is capital S. We could also write this, or we could write this. You'll see different ways of writing it when you're saying that this sequence of partial sums converges. So in general, when you have a sequence, A1, A2, A3, and so on, you can form from it another sequence of partial sums, okay? And in general, they will look like this, First partial sum is just the first term. Second partial sum is the first 2 terms. Then the first sum of the first 3 terms. Sum of the first however many terms, capital N terms, and so on. A sequence of partial sums of some other sequence is called an infinite series. The A sub 1 and the A sub 2 are called the terms of that infinite series. And the limit of that infinite series, if it has one, the limit of the partial sums is written like that. So it's written as if you could somehow add up all of the terms at once. Okay, so whenever you have a sequence, you can form an infinite series from it. So for example, take this sequence here, 1 over powers of 3, general term is 1 over 3 to the n. So you could form, this infinite series. And it is thought of like this: 1/3 plus 1/9 plus 1/27 forever. And you just kind of wonder, like, is that like infinite sum? Is it a finite number or not? Or you could take this little alternating sequence whose general term looks like that. And you could say, what would happen if we could somehow add all those together? What's the limit of the partial sums? And so we could write it out like that as well. So the big question, of course, with these infinite series are going to be, do they converge or not? Does the sequence of partial sums converge to something or not? So let's try it out for this infinite series. Does it converge? And if it does converge, to what does it converge? Well, it turns out with this particular infinite series, we get really lucky. We can analyze it without too much trouble. The reason is the general term, 1 over n times n plus 1. It actually breaks up as the difference of these two fractions. You could check that by just subtracting those two fractions, find a common denominator and then combine. If you didn't know that it broke up into those two fractions, you could still see that it might by doing like partial fractions from previous chapter. Set up an equation where this is like an a over n minus a, plus a b over an n plus 1, and then try to find the a and b, and you'd find that the a is 1 and the b is -1. But anyway, once we've made that observation, then we can actually look for a formula for the nth partial sum. So here I am writing out the nth partial sum. Here I am writing it again, but just using the alternate expression for the term. And here I am writing it out longhand. First term plus second term all the way up to capital Nth term. And when I do that, I notice there's a lot of cancellation. The second part of the first term cancels with the first part of the second term. The second part of the second term cancels with the first part of the third term. And that pattern continues all the way up to the second part of the next to the last term, canceling with the first part of the last term. The only things that aren't going to cancel are the first part of the first term and the last part of the last term. And so the whole sum there, that big sum, actually just like telescopes down to this. You call it telescoping because the 1 and the -1 over n plus 1 used to be far apart, and now whoop, they're close together. Telescopes make things that are far look near. Well, this is great. We have a formula for what the first capital N terms add up to. We just need to take the limit as capital N goes to infinity. So that is what we say it converges to. It's that limit. Here we are looking for the limit, and clearly that limit is going to be 1. Wow. This infinite series converges to 1. I want you to notice that there really are two different things going on here. The sequence itself is converging to 0 as n goes to infinity. The infinite series, being a sequence of partial sums, is doing something else. It is converging to 1. The infinite series is one kind of sequence of partial sums. The terms of it are another kind of sequence. They do two totally different things. How about this infinite series? Does it converge or diverge? Again, let's see if we can find a formula for the nth partial sum. So I try out S1, which is the sum from 1 to 1 of -1 to the little n plus 1. That's a 1. S2 is -1 to the 1 plus 1 plus -1 to the 2 plus 1. And that turns out to be a 1 minus 1, which is a 0. S3 is going to be the first two terms plus what you get by plugging in little n equals 3. And -1 to the 3 plus 1 is a -1 to the 4, which is a plus 1 there. And so now it adds up to 1. And you start to see that you are just going to hop around between 1 and 0. In general, if capital N is odd, then the S sub capital N is going to be a 1, like for the S3 here and the S1 here. But if capital N is even, then the S sub n is going to be a 0, like you saw here for the S2. So the limit of Sn, the limit of the partial sums, does not exist. This infinite series diverges. How about this infinite series? Does it converge or diverge? Well, again, we need to examine the sequence of partial sums. So we look for a general formula for the nth partial sum. Write it out like this, write it out longhand, see what we can get. And here I could use commutativity of addition. I could group the ones together and add them together, and that would be a capital N because there's capital N of those ones. And then there's all those other fractions. And I'm not going to try to figure out what they are. I'm just going to notice that they're all positive numbers. Therefore, this sum here is bigger than capital N. So the sum of the first capital N terms is bigger than capital N. So the limit of the partial sums is plus infinity. It just gets bigger and bigger and bigger. This infinite series also diverges. So I've noticed, like in this case here, the sequence of terms didn't have a limit. Minus 1 to the n plus 1 just cycles between, minus 1 and plus 1. Didn't have a limit. And the series diverges. And here, the sequence of terms had a limit. It's 1. 1 plus 1 over n goes to 1. But it didn't go, the limit was not 0. You were adding on numbers that are getting closer and closer to 1. And so it's like you're adding on more and more ones. And that made that sequence of partial sums go to infinity. So it seems like we've got this. In fact, you could prove this quite rigorously, and they try in the book. They call it the Nth-term Divergence test. If the limit of some sequence is not 0, so I mean either it has a limit and that limit is not 0, or the limit doesn't even exist. If either one of those things happens, then the infinite series that you form from them diverges. Now, I'm wondering about the contrapositive of that if-then statement. The contrapositive of an if-then statement looks like this. Instead of if P, then Q, it's if not P, then not Q. And I'm kind of wondering if this wasn't true, meaning if the ANs had a limit of 0, would it be the case that the series does not diverge, that the series converges? If the limit is 0, is it the case that the series formed out of that sequence converges? I mean, there was a time we looked, when we dealt with the series formed by those terms, we found that that infinite series converged to 1, that little telescoping series, And I'm like wondering, does that maybe always happen when the things you're adding up are themselves getting smaller and smaller? Does that mean the infinite series does have to converge to something? Well, it's not true. The contrapositive is not true. That should say contrapositive, not converse. And the reason it's not true is you can find a counterexample. I can find plenty of sequences that converge to 0, but when you form an infinite series out of them, that you get something that diverges. I'll show you just one example here. Say you look at the sequence a sub n is 1 over the square root of n. That certainly does converge to 0 as n goes to infinity. But let's check out the infinite series, sum n goes from 1 to infinity of 1 over root n. And I'm sorry, I really needed to have a capital N there because what I'm going to do is I'm going to analyze the partial sums. So what would be the sum n goes from 1 to capital N of Sn, of 1 over root n? Well, let's see. Let's write it out longhand and just take a look at it. Well, one thing I notice is that each of these fractions from here all the way up, each of them is going to be bigger than or equal to 1 over root n. Because if I put a root n at the bottom, that's bigger than a root 1, it's bigger than a root 2, it's bigger than a root 3. And so each of the fractions all the way up to 1 over the square root of n minus 1 is bigger than 1 over the square root of n. And then this is just equal to 1 over the square root of n. So this sum here is bigger than just the same number of terms, except they're all 1 over square root of n. And that's capital N of those. And so this adds up to n times 1 over root n. And that's square root of n. So what I'm seeing is that the nth partial sum is bigger than the square root of n. Now the square root of n goes to infinity, so the nth partial sum has to go to infinity. So this infinite series does not converge. So really the situation is not something for which there's like one simple answer or formula for. If you're looking at like a sequence of positive terms, and you're wondering, does the infinite series you make out of them converge? Well, basically, it's not going to converge unless the ANs go to 0 fast enough. 1 over n times n plus 1 goes to 0, and it went fast enough to make the sum of all of them be finite. But 1 over square root of n, even though it goes to 0, didn't go fast enough. So as you kept adding them all together, you ended up with something infinite. Okay, that's all I've got for now. Next time we're together, I'm going to examine another kind of infinite series where it is possible to figure out fairly easily whether it converges or diverges. These are called geometric series. We'll deal with them next time.